Hi, everyone, and welcome to today's MRS On Demand webinar, Dynamic SIMS for Semiconductors from Compositional Analysis of Optoelectronics and 2D Devices to Implant Depth Profiling of Advanced Silicon-Based Structures, presented by CAMECA. My name is Bob Brockler. I'm the Digital Manager at the Media Manager at the Materials Research Society. Today's webinar is being recorded, and it'll be posted to our archive of recorded webinars within a week. Today's event is presented and sponsored by CAMECA, and CAMECA is very much a longtime supporter of the Materials Research Society. You can find them at exhibiting it at all of our meetings and sponsoring any number of events and things with MRS. So we really do greatly appreciate their support. Our sponsors truly are what enable MRS to present this webinar series free of charge. So we are very grateful to CAMECA for their sponsorship and their support. If you look in the lower left corner of this webinar player where it says resources, if you open that tab up, you'll find any number of downloadable documents in there from CAMECA, as well as links to relevant information. And we encourage you to download those as a complement to today's session. We'll get started in just a moment, but first a couple of quick notes about the format of today's event and the player that you're now using. Starting over on the left, you've likely already seen the chat room. Please feel free to use that at any point today to talk to your fellow attendees. Below that, we have the questions tab. Following our talk today, we're going to have a question and answer session. Please use that questions tab to submit your questions. Below the questions tab, you'll see the resources tab that I referenced earlier. In that tab, you'll find contact links for CAMECA, as well as links to our upcoming and archived webinars. At the lower left corner of the player, you'll find the request support button. If you have any technical issues today, use that button to get personalized help to help you resolve your issue. I also want to point out that once our presentation begins today, if you want to see the slides at a larger size, you can click the X that you'll find at the top of the chat room on the left side of the player. Everything on the left side will then collapse and push over, and the slides will expand to fill the screen. Moving over to the right side of the player, you'll see a tab that says Notes. You can click that and take notes during today's presentation. Then those notes will be emailed to you along with all of the resource material immediately following the webinar. Our host today, Kartik Sivaramakrishnan, has a bachelor's in materials engineering from the Indian Institute of Technology, Madras, and a PhD in materials science from the Arizona State University. He started his career as a process engineer at Intel in Portland, Oregon. Thereafter, he was a product manager at LAM Research for their deposition equipment. He's currently the Semiconductor SIMS product manager at CAMECA, responsible for the SC Ultra and Iconis products, among others.
Thank you to MRS and Dr. Michałowski, who is a prolific user of our CAMECA SC Ultra. In this talk, he will give a quick overview of dynamic SIMS basics and then cover some interesting use cases for low energy dynamic SIMS. Which is an area of increased interest in the SIM space due to the move, especially in semiconductors, towards thinner films of a few nanometers, ultra-shallow dopants, and 2D materials, for example, graphene. This talk is based on results obtained by Dr. Michałowski using the CAMECA SC Ultra, but we have since released a newer, more automated tool for analysis using low impact energies called the Iconis, and you can find more information about this product in the hyperlinks associated with this webinar or on the CAMECA website. With that, I'd like to give you a little bit more of a background about our speaker today. Dr. Michałowski was born in Poznan, Poland in 1984. He obtained his master's degree in physics from Umeå University, Sweden in 2007, and Adam Mickiewicz University, Poland in 2008. In 2015, he obtained a PhD degree in physics from Adam Mickiewicz University. His scientific interests focus on secondary ion mass spectrometry since 2007, when he worked at Fraunhofer Center for Nanoelectronics Technology in Germany. And since 2015, he worked at the Łukasiewicz Research Network, Institute of Microelectronics and Photonics, and is responsible for the CAMECA IMS SC Ultra SIMS instrument. At the beginning of 2020, he became the head of the Department of Structural Research and Materials Characterization, which has since been renamed Characterization of Materials and Devices Research Group. Over to you, Dr. Michałowski.
Hello, it's my great pleasure to talk about dynamic SIMS for semiconductors, and it's a great honor that CAMECA invited me to be the speaker of this webinar. At the beginning, let me briefly introduce the SIM technique, which is just a very short, very basic introduction. So the principle of the technique is that we bombard the sample with primary ion beam, and these cause a lot of phenomena occurring in the sample. So as you can see, these primary ions will collide with atoms from the sample, and they will transfer part of its energy to them, knock them from their stationary position, and put them in motion. These atoms will in turn collide with other atoms from this sample. They will also knock them from the stationary position, and so the so-called collision cascade will be generated. Obviously, we will also implant the primary species into the sample. That has to be taken into account with the results interpretation. But the most important things that happen during the analysis are the sputtering and ionization phenomena. So as we can see here, part of this energy transferred from primary ions is brought back to the near surface regions, and so that the sputtering may occur. Additionally, these sputtered species, some of them are ionized. Typically, it's less than 1% of the total sputter species. And these secondary ions will go mass spectral analysis and provide the information about the composition of the sample. There are, however, additional effects that are making the proper interpretation a little bit more difficult. This is the preferential sputtering, so it may happen that one type of an atom may have a significantly higher probability to be sputtered from the sample than the other, and it may cause the formation of a region where we can see clear depletion of one type of an atom and agglomeration of another one. So this is not the realistic distribution of this atom prior to the analysis. This is a SIMS artifact. The other one is the mixing effect. So when we start the movement of all these atoms, as you can see, some of them will penetrate the deeper layers and then can be found in layers where previously there were none of these atoms here located. And also we can see that the effect is occurring in the other direction as well. So we can also bring some of these atoms which were located deeper towards the surface. Of course, this is the asymmetrical effect. We push down more atoms than we bring up. However, the effect may occur in both directions. Okay, so as I said, typically we use the technique for the monitoring of the elemental composition of a sample. Typically, we don't get any information or very little about the chemical state of the sample during the dynamic SIMS analysis. And the most common application is to make a depth profile. So when we continuously sputter the sample, we drill a hole in it, create a crater, and we can not only check what is the elemental composition of the sample, but we can also see how it is changing with the depth. Nowadays, most of the SIMS spectrometers also have position-sensitive detectors, so it is possible to make the lateral analysis of the sample surface, and combining with depth profiling, we can obtain fully three-dimensional images of sample. So in this way, we typically check the stability of layers. We can describe the diffusion phenomena and quantitatively obtain information about diffusion parameters. And of course, SIMS is commonly used for dopant and contamination analysis due to its excellent detection limits, typically below ppm. Okay, and here I would like to show you such a very typical application, very important in semiconductor industry. So here's a depth profile of silicon carbide diode. So we can see a p-type layer where the aluminum was implanted in the silicon carbide material. we see the epitaxial growth of n-type layers doped with nitrogen, and we can continue the profiling up to the substrate. So this is a very thick sample, as you can see, a very well-known application of SIMS and very important to the industry. However, during this webinar, I would like to focus on something else. So what we can say for sure about SIMS, that it's currently not very well known for application in 2D materials. However, as you saw from the title of my talk, I will be showing these examples. But before I can do it, I would like to introduce you to the instrument that I'm using. This is CAMECA Asta Ultra with a picture. This is the actual instrument installed in our lab. So this instrument has two important innovations. The first one is a so-called extreme low impact energy technology. So in most cases, when you would like to decrease the aforementioned mixing effect and increase the depth resolution, the best way to do it is by decreasing the impact energy of primary ions. However, in most spectrometers, 500 eV or maybe 250 is the lowest value where you can obtain a stable primary beam. But in this case, CAMECA used a different approach. So first of all, for the oxygen column, instead of a commonly used duoplasmatron, the radio frequency plasma generator is used, and the impact energy can be reduced to 60 eV, and the beam remains very stable and of high quality. In case of the cesium column, additional floating voltage can be applied directly to the column, and thus we can still keep a very high voltage applied to the accelerator. It can be well above 1 kV. However, we can gradually start to decelerate the primary ions while keeping the quality of the beam, and thus we can decrease the impact energy of cesium ions down to 90 eV. It's worth to emphasize that these are two completely separate primary columns, so the whole optimization of the parameters can be done separately. And the second invention is related to the beam shape. So typically in most SIMS spectrometers, you are working with a Gaussian shaped beam, and as you can see here, the middle part of this beam is a little bit more intense than the edges. So when you think about how such a beam is sputtering the material, so this middle part can go a little bit faster through the material. So you will be integrating the signal from 1 to nanometers. Of course, in an aforementioned example of a silicon carbide diode, it doesn't really matter. We were making a very deep depth profile. This was almost 20 microns deep, so these 1 or 2 nanometers of difference, it's not a problem at all. However, when you start thinking about 2D materials like graphene, which is the thickness is a single atomic layer of carbon, so then the difference of 1 or 2 nanometers is huge when you compare it to the actual thickness of this material. So this is no longer acceptable. So in this case, CAMECA designed 2 square stencils that you still take this Gaussian shaped beam and project it on these stencils, so that in the end you end up with the rectangular beam, which is just taken from the middle of the Gaussian beam. So as you can see, it's very uniform and of high intensity, and such a beam can sputter the material very homogeneously. So in this way, it is possible to go atomic layer by atomic layer. However, at that point, I would like to emphasize that when you start to using such a low impact energy, you will have a problem with the intensity of measured signals. So from that point, let me emphasize that the proper calibration of the tool is extremely important. So basically everything should be perfect if you want to obtain high quality results. So you can't allow any inhomogeneity on your primary beam. Everything needs to be very, very well aligned. Okay, but the problem is that these two inventions are still not good enough. So I created something that I call the dedicated procedures. So basically, we do have very standard or universal measurement procedures that you will get when you order the instrument, and you can create something that, as I said, these are the dedicated procedures. So what is the difference? The universal procedures can be used for virtually any type of material, and they are optimized in this way to maximize the total amount of registered ions. So here, as you can see schematically on this picture, this green cylinder is showing the which of the emitted secondary ions will be extracted and collected. So as you can see, the total amount of registered ions is maximized. However, if you look closely, I marked some of the secondary ions with blue dots, and as you can see, only just a few of them will be collected in this standard procedure. So the trick of the dedicated procedure is to re-optimize the extraction parameters so that you will focus it on the some specific type of signal that is most interesting for you at this moment. This is a little bit complicated, more time consuming, but as you can see, we will still lose some intensity of other type of atoms, but this should be still enough if we decrease even 2 orders of magnitudes, but we will also increase the intensity of desired signal. And the trick is that during your analysis, you can do this optimization of extraction parameters separately for different ions. And in this way, you can obtain the highest quality information about your samples. So, okay, let us start with graphene, aforementioned graphene, so a single layer of carbon atoms in here grown on germanium substrate. The depth profile that you are seeing is a very standard 250 eV impact energy procedure with 45 incident angle. What we can see here is that the graphene is actually sputtered only after 4 data points. And we see that there are a lot of contaminants in here. The reason was that the reactor used to grow this graphene was also used to grow molybdenum and tungsten sulfides, also graphene on copper, and the sodium is probably related to the contamination coming from air in form of salt. So clearly we can detect these contaminants. We get a pretty good detection limits, even below 1 ppm. But this is very hard to interpret where exactly these contaminants are located. As you can see, this signal has a really long decay length. And it's hard to say whether these are located on top of graphene, are incorporated here. And what is the actual problem? We only gather 4 data points here, and a lot of mixing effect, probably a lot of the preferential sputtering. The heavier elements are not sputtered efficiently. They are pushed down all the time before they can be sputtered. So how to solve this problem? First, we need to identify what are causing this impossibility to interpret the results. So first, the transition layer. Typically, the first few data points of a SIMS depth profile should not be counted as reliable. However, in this case, the problem is that these 4 first data points, it's all we have for graphene. So what we can do is to lower the density of the beam. However, in this case, we will drastically reduce the intensity of register signal. And to counter it, we should increase the integration time of these signals. However, then we will still end up with just a few data points for graphene. Similarly, to reduce the ion mixing, as I said, we can decrease the impact energy. But once again, this will decrease the intensity of all measured signals. So once again, we should counter it with the higher integration time, and we'll end up with all the same, just a few data points for graphene. And then there is a problem with the preferential sputtering. As I said, heavier elements are not sputtered efficiently in this mode. So we may use the higher impact energy, but this will obviously cause the bigger ion mixing. And we don't really have a any feasible solution to that. So my idea was to change the incident angle of the primary beam. So increase it to 75 degrees. And in this type of analysis, only roughly 1 out of 1,000 of primary ions is actually causing any sputtering from the surface. Most of them are completely reflected from the sample for such a high incident angle. So how does it help me to obtain a better result? So first of all, for increasing this impact energy, I start to making this analysis very slow, and I can get even 30 data points for graphene layer. The transition layer problem is no longer effective, so this problem is eliminated. So the actual momentum that these ions for such a high incident angle are transferring directly to the which are perpendicular to the sample surface is very small. So the ion mixing is actually eliminated as well. And the preferential sputtering too, because this atom has nowhere to go. So we don't transfer, we don't put them into motion, so we can't push them deeper. So sooner or later, they will have to be sputtered from the sample. And the only actual disadvantage is that we increase the acquisition time quite a lot, but this is some kind of a sacrifice that I was willing to do. So as you see, the previous depth profile was obtained within 5 minutes and the enhanced in 3 hours. However, please note that the actual detection limits are getting just a little bit worse. So how does it look like for the enhanced procedure? Here's the depth profile now. And now you can see that indeed we get more than 30 data points for graphene. We don't really care too much about the transition layer. And now we eliminated the mixing effect and preferential sputtering problems. So now we can really see the actual distribution of these contaminants. So first of all, we see that there is some sodium and sulfur on top of the surface. So as I said, this is probably coming from air. The molybdenum and tungsten are located exactly on the interface between the germanium substrate and graphene. This is not surprising because, as I said, this reactor was contaminated with these metals. So they were just deposited on the germanium substrate. We can also see that some sulfur passivated the germanium substrate, so this is a very well-known effect. And the most interesting part is with the copper. Now we can see that it is fully incorporated into graphene layer. So now we can not only detect these contaminants, but very precisely localize them. We can also integrate the sodium and copper signals and to see the lateral distribution. So in case of sodium, as you can see, this is a very homogeneously distributed on the surface of graphene. However, in case of a copper, we can see that there is some points where are more copper. So probably that means that locally there is a copper graphene composite on this sample. Okay, now I will switch to more much thicker sample. So this is the structure of vertical cavity surface emitting laser. So it consists of hundreds of layers, and there are just some quantum wells which are 3 nanometers thick. We can have some oxidation aperture here. And this is a very difficult sample to be measured with SIMS. And once again, I will start with a standard procedure to show you such a depth profile. So here it is. We can see the aluminum and indium signal. Indium gallium arsenide quantum wells were located here. However, when we zoom in, we can see that we can't really distinguish these 5 quantum wells. So there are quite a lot of problems here, because in theory, it may happen that this distribution of aluminum is realistic. As you can see, the growth direction was, of course, opposite to the analysis direction. So these layers were grown first, so they were under the thermal treatment for the longest time. So it is possible that they blurred a little bit during this analysis. However, in this case, I was afraid that this is the SIMS-related artifact, and I identified the problems. So first of all, once again, we have the problem of the mixing effect. And then for such a long, thick sample, the problem is that the roughness of the crater's bottom is increasing during the analysis. So that's also making this problem. This is the long measurement, so the primary beam may deteriorate, and thus we end up with a very poor depth resolution. Well, so to say, very poor. But I was not satisfied with these results, so once again I established the dedicated procedure. And here it's getting quite complicated, because once again, what can we do? So the mixing effect, once again, if we lower the impact energy, then the preferential sputtering and crater roughness will increase. If we use higher impact energy, which typically reduces the problem of the crater roughness, we will increase the mixing effect. With the primary beam deterioration, if we go faster, so we use the higher beam density, then this problem of deterioration will be reduced. But once again, we'll end up with poor depth resolution. And how to even solve it? So the question was, once again, is it even possible to optimize this procedure? So here I thought that we need something completely different, a completely different approach. So as you know already from the previous example, I'm a very big fan of high incident angle experiments. They are very difficult to optimize, but still it is possible to reduce the mixing effect. Then I said that for the crater roughness, we need the ion polishing, which I will be showing you in a minute. And for the primary beam deterioration, we need a beam service, and to increase the depth resolution, we need the impact energy modulation. So let us start with the extraction parameters, and this is something that I already mentioned during this schematic talk about this optimization of these parameters. But here I will show you a very good example. So when you use a very standard procedure, it doesn't actually matter which secondary ion you use for the extraction optimization. Here you can see the example. Typically, the extraction parameters optimization is done on a silicon test sample. And as you can see, the intensity of the indium, gallium, or aluminum signals for these standard procedures is just a little bit lower when they are optimized on silicon substrate than when they are optimized for secondary ions, which are, indium for indium, gallium for gallium, and so on. So we only lose a few % of the intensity when we optimize these parameters on the silicon substrate. However, when we switch to the high incident angle bombardment, the situation is completely different. As you can see, this is not possible to optimize these parameters on silicon substrate. You can lose more than 2 orders of magnitude of your intensity. So it becomes clear that you have to optimize the extraction of secondary ions based on this ion. So when you want to detect indium, you can't use silicon substrate. You have to use the substrate for which contains indium, and the same for all the other elements. There is one problem, however, that currently the software does not support this change of the extraction parameter during the analysis. So to solve it, I simply had to program it as a chain analysis. So the software is interpreting it as that I'm making a series of separate experiments when I'm switching these extraction parameters. So the little problem is that I can get one data point per file. So creating a full depth profile, and I can end up with like 20 or 50,000 of files. So trust me, you need a script to compile it again after the analysis. But it got me thinking that since I'm already making these interruptions, so I'm making the every data point is absolutely separate, I can do a lot more than just to adjust the extraction parameters. So I thought that, okay, I can also modulate the energy during this experiment. I can modulate the incident angle, even the polarity of the detector, whatever I want. And I can also include the additional steps during the analysis. So here are some few ideas that I incorporated in this procedure. So as I mentioned already, to counter this roughness, I also include the ion polishing. So basically I use the quite high energy for primary ions for coming through with the very high incident angle. And in this case, most of this momentum is parallel to the surface. When I additionally add some offset voltage, it's making it impossible for this primary ion during this ion polishing stage to interact with the sample. So I will not cause any damage to the sample. However, if there is some kind of a residual contamination, some kind of a roughness, you can see that there will be a direct hit with this primary ion, then this will be simply removed and cleaned. So I incorporated that every half an hour or something like this, I make this polishing of this crater. Then I also realized that here you can see that right after the beginning, the beam is the primary beam is switched on, the intensity increases, then it's quite stable for a few hours, and then it slowly starts to decrease. So I set a very safe value, so like 15 nanoamps. And once again, during this polishing, I was also making fully automated service of this beam so that it stays as this desired value. So did it help? Yes, it did quite a lot. So this is the final result of this complicated measurement procedure. As you can see, now I not only include aluminum and indium signals, but also gallium and dopants and contaminants like carbon, silicon, and oxygen. And now we can see a very perfect structure here. And if we zoom into this quantum well region, so we can still see that we can get a very perfect separation, and we can see all of them. So the trick here was that very close to this quantum well region, we simply decrease the energy to decrease the mixing effect and made the measurements of these wells very, very slowly. So how important was it? I would say that quite a lot, because if we didn't do it, that's the zoom on this quantum wells. They are registered, they are well separated, so this is a very nice SIMS result, but I'm pretty sure that you don't see any defects of this quantum wells, and we intentionally introduced some defects in here. So now if we switch this energy modulation, so this quantum well region is registered with much smaller impact energy, we can see the real picture here. So first of all, this quantum wells is a little bit thicker than the other one. This one contains more indium, and here this quantum barrier is a little bit thinner than the others. So this can be achieved only by this energy modulation. Okay, staying with this VCSEL structures, we also saw that after the after the processing, some of these structures were operating quite nicely, others were completely dead, and others were just showing just a very weak luminescence. So here we can also apply the failure analysis with the three-dimensional imaging. I'll be showing it as a cross-sectional view. So first of all, let us see how the oxidizing layer is forming the aperture of such a laser. For a good laser, we can see a very nice formation of this aperture. So we basically get the operating laser. In those which were not operating at all, we saw that the oxidation process was too fast, and this oxidizing layer oxidized through the whole sample. And in these lasers that were just showing the very weak luminescence, we saw that we did form the aperture, but there was also the oxidation of the full structure coming from the surface. And obviously it reached the quantum well region, and thus the laser action is not present here. Okay, staying with the quantum wells, I would like to show you very beautiful examples of the analysis. This time, this is indium gallium nitride quantum wells with similar barriers, just with the much smaller indium concentration. So here is the typical problem of growing such a laser, is that there is a huge lattice mismatch between indium nitride and gallium nitride. And the other one, that growing of the indium nitride requires typically lower temperatures. However, to grow the p-type GaN on top of the structures, it's better to use higher temperatures. So here you can see the optical power, particularly for these samples. As you can see, it's very low for when the p-type was grown for in low temperature. It starts to increase for higher temperatures, but after some point it suddenly decreased quite a lot. So we can also make the three-dimensional images of these quantum wells, and here is the results. For the lowest temperature, we can see that there is a lot of indium concentration fluctuations within this quantum wells. Please note the scale, that this is not like a TM image, because this is only 30 nanometers here, but 200 microns in this direction. So these fluctuations are actually macroscopic. And we can also include the nitrogen analysis, so we can see a very homogeneous distribution as it was expected. In higher temperature, this operating very well. You can see that the homogeneity of these quantum wells is very, very good. However, in the bottom quantum well, we can see some metallic indium precipitation, which is additionally confirmed by the depletion of nitrogen in the same region. And for this highest temperature, where we already saw that the optical power of this laser was dropping close to zero, we see a very beautiful picture of a decomposition of this bottom layer. So we can, well, I think this picture speaks for itself, but we can also see that there is some regions here that we can detect more nitrogen than anywhere else, which suggests the formation of nitrogen bubbles. And we already see the start of the decomposition of a very early stage of the second quantum well. So just a very short summary. So we can confirm the microscopic fluctuation, metallic indium precipitation, formation of these nitrogen bubbles, and we can see that only one interface is affected, the bottom one, every time. And we related to the vacancy out diffusion from the lower regions towards the surface during this growth of the p-type gallium nitride. Okay, so for just a short conclusions of my talk, I showed you that I'm using the state-of-the-art instrument, but to get the very nice results, dedicated procedures are needed. They are very time-consuming, both to establish them and then to use them, as you saw, but this is totally worth it. And in this way, we can really reach the sub-nanometer or even atomic depth resolution during the SIMS analysis, which enables enables 2D materials characterizations. I may also at the end conclude that please remember that I'm not giving up yet. I'm still trying to improve my procedures, and I do it all the time. So I always hope to get better and better results. But clearly, this approach with these dedicated procedures is already providing me some superior results which can't be achieved otherwise. And with that, I would like to thank you for your attention, and I'll be waiting for your question in the Q&A session.
Hi, everyone. Hopefully you found that talk from Dr. Michałowski as enlightening as I did. We have Dr. Michałowski on the line and ready to take questions. So the first question we have from the audience is, how low in impact energy are you able to reliably analyze using the low impact energy column of the SC Ultra? And as a corollary to that, is it possible to detect hydrogen with low energy SIMS?
Okay, so basically the lowest energy we can get the beam to be stable and of high quality, it's about 60 eV for the oxygen column and 90 eV for cesium column. Hydrogen would be then detected with cesium, and in negative polarity, it is possible to detect hydrogen in this mode. However, the detection limit gets much worse than in typical measurements. So then you should probably use a so-called pre-sputtering. For that, basically, it means that for like 20 hours, 50 hours, you may sputter a clean material to cover the immersion lens with something. Typically, we use silicon for this. However, quite recently, I published an article where I showed that when you pre-sputter the metallic titanium block, you can obtain much better detection limits. So it's slightly below 1 × 10 to 18 atoms per square centimeter. Obviously, it's not as good as it is for standard measurements. However, this is still may be acceptable.
Thank you, Dr. Michałowski. The next question that we have is, how do you measure the depth of the signal in dynamic SIMS? And what is your assessment on the accuracy of this measurement?
Yeah, this is really typically very tricky to make the proper depth calibration. So for simple samples, the best way to do it is to measure the depth of your crater, and then you can see what was the etching rate, and then you can recalibrate the profile. However, when the sample is quite complicated and it consists of many layers with different compositions, it can be very, very tricky to do it in this way. However, what I showed in the for the results for the depth profiling with a very high incident angle, as I said, in these cases, typically only one ion interacts with the sample, and I found that in most materials have very comparable etching rate in this case. So then it is possible to measure the depth of your crater and simply adjust the whole measurements with this, because there will not be many big changes in the etching rate.
Okay, very good, Dr. Michałowski. The next question we have is, maybe if you could provide some insight in terms of the potential for using machine learning in SIMS data processing.
Oh, I haven't used it yet, so I'm definitely not a specialist. So I hope to start a cooperation soon, and it will be especially needed to properly recreate the depth profiles, the 3D dimensional reconstruction of depth profiles, because sometimes during the analysis it may the picture may a little bit misalign. the following layers. So I would say that the machine learning would be very helpful to make this three-dimensional reconstruction. However, I must admit I'm not an expert here and I've never done it so far.
Okay, thank you, Dr. Michałowski. And then one of our audience has said, thank you very much for your rich and pertinent presentation, and followed up with a question in terms of how the ion probes, how you can use certain ion probes and how they affect the persistence of the artifacts that you identified in dynamic SIMS.
I'm not sure I understand this question. So maybe if you can elaborate a little bit more.
So the question is essentially to reiterate on the general artifacts that are known to occur during dynamic SIMS.
Okay, but which artifacts in particular? So during my talk, when I was showing the results for graphene layer, I identified some artifacts, and then as I said, the high incident angle bombardment usually eliminated most of these problems. But I'm not sure if what kind of other artifacts you may have in mind. Maybe I can also elaborate that it's a little bit more difficult to for the 2D materials to make a proper concentration calibration when we want to quantify the contaminants. As you saw in my presentation, I was using some standards to do it. So basically, to say simulate the graphene, I use the graphite, thick graphite, highly oriented periodic graphite, and then I implanted with ions of these sulfur, copper, sodium, and these metals that I was covering there, and made the concentration calibration based on these. I would say that this graphite emulated the graphene layer quite nicely. No, but obviously this is still it can be affected by the matrix effect. So the precision of this contaminants level that I was discussing during the presentation may not be as good as in other materials like silicon or silicon carbide that I showed earlier.
Okay, very good. Thank you, Dr. Michałowski. That's all the questions we have from the attendees today. And thank you to the attendees for listening to Dr. Michałowski's talk. It's over to you, Bob.
Thank you so much, Karthik. And thank you to our speaker and to our audience as well. But we did just get one more question in, Karthik, if you want to take that one.
Oh, yep. Sorry, I just saw the question. There's one that says, great talk for the quantum well nanostructures described here. Is the old sample rotation method useful to improve the depth resolution at these length scales?
The sample rotation, but then it wouldn't be very well possible to obtain the three-dimensional image, because I would say that it would make it at least very difficult. And I may also mention that the tool that I'm using, the sample cannot be rotated during the analysis. So I'm not perfectly sure, I would say.
Okay, I think that is all the questions. Is that right, Bob?
Yeah, that's it. That's
okay.
It. Okay. Thank you once again, Karthik, and thank you to our speaker and audience as well. We want to remind the audience once again that there's a link to the CAMECA website, as well as quite a lot of supplemental material in the resources section of this webinar player. Dr. Michałowski also provided a document about his research group that's also in the resources section and well worth checking out. We also, if you haven't downloaded that material yet, don't worry about it. All of the resource material is going to be emailed to all of our attendees in just a few moments. Also, I want to take a second and thank Kaylee Brunacini. She is our producer for these events and always does a marvelous job for you. So I want to make sure to thank CAMECA for sponsoring today's event, as well as our recent event. This is the second of 2 CAMECA webinars that we've done recently. The first one was called New 3D Nanoscale Research Breakthroughs by Atom Probe Tomography. And I've put a link to that one, the archive of that one, in the resources as well. Definitely, it was a great session, and we encourage you to check that one out as well. Our sponsors really are what enable us to keep this webinar series free of charge. So we certainly do encourage you to find out more about CAMECA at CAMECA.com or by downloading the material provided in the resources tab. An archive of this webinar will be posted to mrs.org/webinars within a week. I remind you once again that the resources tab contains a link to all of our archived webinars, as well as a link to where you can register for all of our upcoming webinars as well. And in fact, I should note that next week on Wednesday, we have an MRS Bulletin webinar on materials developed for specifically to battle the COVID-19 pandemic. So I think that's going to be a really interesting session. And then later in September, for those of you for whom a green card to work in the US is in your future, we're going to have a session with an attorney that will help illustrate the path to obtaining a green card. So I realize that's kind of a niche audience, but if you're interested in that, I suspect you'll be very interested in that particular session. So thank you once again to our host, to our speakers, and of course, thanks to all of you for attending.